Hello, we are the GPS Spoofing Defense Group, and our senior design project is based on detecting GPS spoofing. These types of attacks involve a transmitter, often using a software-defined radio, or SDR for short, and they interfere with GPS devices. Since SDRs are pretty low cost and require little knowledge to operate, an attacker can transmit inaccurate coordinates and interfere with civilian devices that use GPS. In one case, a GPS spoofing attack interfered with a Tesla's autopilot feature, and this caused the vehicle to exit an expressway prematurely. And so this brings our senior design group's motivation to develop a GPS spoofing defense system to mitigate the risk of a potentially deadly GPS interference. Our methodology involves 4 steps. The first was simulating spoofing attacks using a software-defined radio called LimeSDR. We used ephemeris data, which contains information on the timing and location of satellites from NASA's website. We were then able to convert that ephemeris data into a binary output files using an open source software called GPS SDR Sim. Those new binary files are then used to simulate a GPS spoofing attack by running the files on our LimeSDR, and we were able to successfully change the location of nearby smartphones and a GPS module in a closed environment which did not affect devices outside of our group. After successfully simulating a GPS spoofing attack, we then used an Arduino Uno and a GPS module called the Neo6M to collect and analyze GPS data. Figure 3 shows the schematic and the snippet of code that ran on the Arduino Uno. A sample of the output from the GPS module is shown in Figure 4. The output contains information about the GPS signal like latitude, longitude, the number of satellites in range, and the signal-to-noise ratio. We've collected data from normal GPS signals and spoof signals from the LimeSDR, and then we parsed it into formatted files so it's easier to analyze. We decided to use a classical machine learning algorithm for classification called K-nearest neighbor, or KNN for short, for defense. It is based on feature similarity, meaning that GPS signals will be classified as authentic or false based on how similar GPS data is to normal signals or spoof signals. While analyzing our collected data, we noticed a large difference in the signal-to-noise ratio between normal GPS signals and spoof signals. You can see the difference in Figure 5. It shows the average and standard deviation of SNR values from authentic and spoof signals. You can see that normal GPS signals have lower SNR values and slightly higher in standard deviation. Figure 6 shows the average and standard deviation plotted on the x and y axis. This shows that SNR values can be used to distinguish between true normal locations and false spoof locations. We've also looked into the number of satellites in view and the number of satellites being tracked and added those to our KNN algorithm as well. To test our KNN algorithm, we implemented an Android application using the Google Maps API to display your current location. You can see in Figure 7, it shows a screenshot of the app running on an Android phone emulator. So whenever a spoofing attack is detected, the application displays a pop-up notifying the user of the attack. We then tested the KNN algorithm and it was able to classify new data as true authentic locations or spoof locations with over 99% accuracy. We measured the precision recall and F measure, as you can see in Figure 7, all achieved by 99% accuracy. The decision boundary in Figure 8 shows the algorithm's predictions of each input based on the shaded region it's in. You can see that majority of the GPS signals are correctly classified with the exception of a few. Our senior design group has been able to successfully spoof GPS signals using a LimeSDR. We use the KNN algorithm to successfully detect faulty signals. We've integrated that algorithm into an Android application. We've tested the accuracy of the KNN algorithm, which achieved above 99%. And we tested the Android application, which has been able to successfully detect those faulty signals as well. In the future, we would like to develop applications to be able to defend against different types of GPS attacks. And we would like to further develop our algorithm to ignore faulty signals. And this would allow a device to correctly operate while being spoofed. Lastly, we want to give our thanks to our academic advisors for supporting us throughout both semesters of senior design. And we want to give an acknowledgement to the Space Grant for supporting us and helping us purchase all the materials that we needed for our project.